All right, our next speaker this afternoon is Malena Bloom, who's joining us this summer from UCLA. Malena's been working with Jack, and today she'll tell us about their project together, searching for contamination with CarLS Jr., characterizing calibration lamps for use in ViaSpec.
Thank you, Gwen, and thank you everyone for coming. Before I get into the meat of my project, I want to talk a little bit about why it seems like I'm about to talk about a fast food chain. So just to kind of give you kind of an overview of the project structure, I was working in instrumentation this summer with Jack, and my project was part of the larger VIA project, which I'll go into a little bit more later. ViaSpec is one of the instruments going into VIA project, and CarLS Jr. is like a testing bed for data reduction of ViaSpec. I'll kind of go into what that means a little bit more, but CarLS Jr. and ViaSpec are both instruments. CarLS Jr. is the one I'm working on. With that out of the way, I can kind of talk about what the VIA project is and why we're spending a lot of money to do it. The VIA project has 3 primary science goals, and it's an instrument suite that will attach to MMT and Magellan telescopes to accomplish these goals. So these science goals in particular are first to find and constrain the mass of low mass dark matter halos using stellar streams. So this blue line represents a stellar stream, and this lighter blue dot represents a dark matter halo. The theory is that when the dark matter interacts with the stellar stream and just kind of runs into it, it produces a gap which will change the velocity of the stars within that stellar stream. So if we have instruments that can take really high precision radial velocity measurements of these stars, we can constrain the mass of the dark matter halo that originally interrupted the stream. The second goal is to probe the nature of low mass galaxies. So we see here this top image is actually just a cluster of stars, and this bottom image is a dwarf galaxy. So what we're really looking at is ViaSpec has a series of dwarf galaxy candidates, and it will be using dynamic masses to distinguish between whether it's just a star cluster or whether it is actually a dwarf galaxy. And using that collection of dwarf galaxies, we can then find how large a dark matter halo needs to be to eventually form a galaxy. Finally, we want to probe the structure of cold circumgalactic medium. This is just a random gas cloud. We do not have pictures of cold circumgalactic medium, but the underlying principle is that using Milky Way stars as backlights for the gas in regions that are particularly dense with these gas backlights, we can form a 3D topographic map that is both spatially and velocity resolved for this cold circumgalactic medium, which should help us probe stellar evolution. From there, we have 3 instruments to accomplish these goals. It's 2 spectrographs and 2 spectrographs for each telescope, and also a series of over 600 fiber optic slits, each of which are positioned on robotic actuators, which allow them to be accurately positioned towards different parts of the sky, so we can look at 600 different objects at a time. Boombox is the smaller of the 2 spectrographs and the one I'm less involved with, so I'll go over that first. But as you can see, it has 2 optical benches, one of which is for red wavelengths and one of which is for blue. It's a pretty low resolving power and a large wavelength range, at least compared to ViaSpec. ViaSpec is the one I'm actually more affiliated with, but ViaSpec is a much higher resolution. It's specifically focused on targeting the radial velocity measurements that I talked about that are important for all 3 science goals that I talked about last slide. And it's operating over a very, very small wavelength range. And this is because this is where we want to examine for the science goals. So with that, we can see CarLS Jr., which is the Carnegie Lab spectrograph, or ViaSpec Jr., named after the fact that it is made of many of the same materials. It's just like a smaller version of ViaSpec. It should have the same resolving power and the same wavelength range. So here are all the parts of CarLS Jr. The only one I really want to talk about here is the diffraction grating, which is the element that actually separates light based on wavelength. Ours uses a binary diffraction grating, which has a higher throughput than a traditional grating, and is just it's like a step function instead of a traditional grating, which is kind of interesting. But if we want to follow the light, we can see you can kind of tell what's happening here. It's a relatively traditional spectrograph in a lot of ways, but you can see where it gets separated. And this was what I spent the first half of my summer building. So my project was mostly in 3 parts, the first of which was to work with Jack and one of the engineers in the lab, Julian, to actually construct this device. To talk about the motivation for the actual, after we built it, what are we doing with CarLS Jr.? Why did we build a second spectrograph before ViaSpec? There's some things I want to talk about. First, this equation on the right kind of gives you what our centroiding accuracy needs to be in order to actually do the radial velocity measurements we need to make. And this defines how accurate our wavelength solution needs to be. And CarLS Jr. is kind of helping develop how we build this wavelength solution every time. So you can see ultimately we want to be able to centroid peaks within 0.014 pixels. So the way you usually calibrate these kinds of devices is using thorium-argon lamps because they have a lot of lines in a very relevant wavelength. And this NAVE paper showed that these lamps are actually contaminated due to changes in manufacturing. So counterintuitively, the green is the bad lamp and the red is the good old lamp. But you can see these boxes here are characteristic contamination peaks. So throughout the slideshow, if you can look for those, it's a top stark increase and then a slow tapered decrease. That is thorium oxide contamination in our thorium argon lamp. You can also see, as we're going to go through later, it changes a lot of the characteristics of the spectrum. So from there, we bought 60 thorium argon lamps and we started to develop a data reduction pipeline. This was kind of the second stage of my summer work. So the first part is to take a lot of raw data. So far, we've only taken from 6 lamps. We have 60, but we do it in a relatively normal way. You take bias frames, lights, darks. Then you add them all together separately and take the median, and then you do some subtraction to get rid of any systematic noise. That's how you get this image. And then you can see this white line through the middle. It might be hard to see in the back, is actually a straight line. So our spectrum is not straight. So we just did a tilt correct for that. And from there, this program called SpecReduce takes a slice of about 20 pixels through the center of our corrected spectrum, and it averages along straight lines through that 20 pixel range and can give you the relative intensity versus a pixel value. So if any of you work with spectra, you may notice that this looks really similar to what you might work with, except we have pixels in the x-axis, and that's not very helpful. So from there, we need to do, our next 2 steps are focused on finding a wavelength solution. So from here, we centroid our peaks because we can only find peaks within 1 pixel values, but we need to centroid to 0.014 pixel values. We take the weighted mean of each peak to find a mathematical center that's a little more accurate than your traditional like SciPy find peaks. And once we have that system, we did this actually on a uranium neon lamp to independently verify our wavelength solution because we didn't want to use contaminated lamps to figure out our wavelength solution. So we used a uranium neon lamp and we compared it visually with NIST lines. We could find the matching lines and we could map the pixel versus wavelength value using a cubic regression. We then apply that to the thorium argon lamp and we use just a couple of really easily distinguishable lines in our thorium argon lamp to kind of shift the spectrum if it needs to be shifted at all, the wavelength solution if it needs to be shifted at all. But from there, we should have a pretty solid wavelength solution. So once we did that data reduction, we could actually just find some specs of our device. So our resolution element, which gives us kind of how wide of a peak that we get, is approximately 0.26 angstroms. And our resolving power is actually higher than it needs to be. We're aiming for, again, 15,000, which is the same as ViaSpec, and we got 22,000 for our resolving power. From there, we can get to the actual science of my work this summer, which is pretty interesting and not at all what we really expected to see at the beginning of the summer. So like I said, we've tested 6 lamps so far. These are all run at the same current, at the same time from the same manufacturer. The whole point of these lamps is to be the same, to be consistent across different devices. And as you can tell visually, they are not the same, which we were expecting some contamination from the NAVE paper, but not to a level that you could tell so visibly with the naked eye. But as you can see, our high contamination peak, which is the top here, has consistently higher background, which makes it harder to distinguish peaks than our lowest contamination. And all 6 lamps kind of spanned this range. They were all different in terms of how contaminated they were. So how do we quantify this difference? We use relative flux comparisons. So like I said earlier, we see our characteristic contamination peak here with that sloped decrease. A couple other things to notice about this graph is that our lowest contamination peak obviously shows the lowest contamination peak, but it also shows a low normal thorium argon peak over on this left side, but a high thorium argon peak on the right side. So what that is giving us evidence to is that contamination is affecting different peaks differently, which is problematic if we are trying to figure out how to centroid our peaks super accurately. So this is just a 12 angstrom range, I think. We can see this applies to the entire spectrum. So a couple things to point out. Again, we see that the high contamination lamp is consistently higher background and blocking out lower background. We can also see that the highest peak is generally the blue, but not always, which is our low contamination. And so we just generally see our entire spectrum, the flux, the relative intensities being changed from how we expect it. To quantify this in a slightly different way, we can take the ratio of our more contaminated lamps to our less contaminated lamp, and we can see this very easily quantified in a background that's about 2 to 3 times higher in our more contaminated lamp, and significantly lower molecular peaks here, and a slightly higher molecular peak over there. Or not molecular, atomic peak. So what does this mean? Ultimately, our goal for ViaSpec is to create a list of stable lines. Because one thing I'd like to point out is like this entire graph would be resolved as one peak in ViaSpec because our resolving power isn't that high. So if one peak shifts more than other peaks, it's shifting our centroid because all of this is resolved as one peak. And that's what's ultimately problematic, is we'll see unstable peaks, which kind of eliminate the purpose of a wavelength solution and these calibration lamps. So ultimately our goal is to find a list of stable peaks that can be used for the calibration of ViaSpec. So that next steps, in addition to making this list, is to quantify the relationship between line ratios and contamination. If that relationship is consistent, then we can still use these lamps as usual, as long as we can like kind of know what we expect. Then the second is to determine whether line ratios change over lamp lifetime. This is really important. So a already well-documented phenomenon is that argon peaks decrease over lamp lifetime because the pressure in the lamp decreases, and that affects argon lines pretty heavily. So if it affects argon, we don't know how it affects thorium oxide contamination. So are our lamps going to change over time is something that's going to be really important when it comes to centroiding our peaks. And finally, we want to identify additional molecular features. All of these are listed by NAVE as possible molecular features, and there's something for us to look into to find kind of support for both of these future findings. And that's it. Thank you all for listening.
All right, questions for Malena?
So are you mainly concerned when you're talking about the peaks shifting? Are you mainly concerned about horizontal shift or the vertical shift?
The vertical shift is like interesting and also kind of annoying because a lot of cross-correlation functions use the intensity, but it's not necessary. The most important is the horizontal shift, which has to do with, again, like the difference in how peaks are affected.
Other questions? Gotta get my steps.
This is very cool. I'm a bit worried though. Do you think we need to now replace all of our thorium argon lamps in all of our spectrographs?
Ultimately, like ViaSpec has spent $60,000 on thorium argon lamps. We're going to use them. It's just like we need to understand them better. So now, like the paradigm that we've been operating on is that all of our lamps are the same, and that's no longer what we can use. So ultimately, the goal is to still use them, but we want to understand if the way we use them changes at all. It might be, I think you do exoplanets, it might be a bigger deal for them because the wavelength solution needs to be a little bit better because of the higher resolution, but yeah.
Thank you for seeing me.
Other questions or fears?
I was just curious because you, I think, mentioned you have a different lamp. Was it uranium neon or something for kind of like calibrating? Is there a reason we don't use those for like our main like lamp?
So if I find like a normal spectrum here, this is a thorium argon spectrum, and the reason we use it is because it has a lot of lines over this green wavelength range. Most of the uranium neon lines are on the far end, which are technically outside of our wavelength range, but Carl's Jr. just happened to be a little bit wider than it needed to be. And we don't have enough lines to get as accurate a solution as we'd like. We only, like when I run I usually only limit peaks to like a smaller flux. I only find like 8 peaks in the uranium neon. So it just doesn't provide the accuracy that we want.
Yeah, thanks.
Okay. We'll do one more.
I mean, this is a question that's less about the science and more just the practicality. Just wondering, like, is anyone talking with the manufacturer of these lamps to tell them about these issues?
So there's only one manufacturer, so we don't really have much to do.
Hence why I'm asking.
Yeah,
like.
So the reason, to my understanding, that they've changed is that thorium was recently classified as a nuclear material, and the company that we usually get them from stopped making them because that was an annoying hassle. So now there's only one company, and so I think they know they're contaminated, is my understanding. Like, it's been published that they're contaminated. There's just not much we can do about it because we don't have other options.
So I guess it matters if enough of their customers care that it's contaminated.
Yeah.
All right, let's thank Malena again.
Thank you.